So the title of the talk is Sum of Squares, as Avi guessed, quantum entanglement, which I know almost nothing about. And log rank. And this is based on a joint work with Boaz Barak and Pravesh Kothari. Which hasn't appeared yet, but I'll talk about it anyway. So I want to start with telling you about a meta problem which is behind many of the questions that I will discuss during the lecture. And so it's a very simple, basic question. Suppose you have a quartic form. So that's just a homogeneous polynomial of degree 4. So f of x. And over Rn. And so the problem I want to think about is, can you maximize f of x subject to being on the sphere, x having Euclidean norm 1, and there are different names for.
Rn is R4.
Sorry?
Is Rn R4?
No. So 4. So sorry. This or was there some problem with it? So here I'm just writing a generic homogeneous degree 4 polynomial, and right, there are n variables that take real values, and what I'd like to understand is the problem I want to look at is to maximize this the absolute value of this function over the unit sphere of Rn. Now notice that if I had a quadratic form here, then this would be the largest singular value of the matrix corresponding. Now you would have just two indices, and you would try to compute the largest singular value of this. And of course, like if you choose f of x to be so this generalizes, and like this problem is more general. So largest singular value. If you choose, for example, f of x to be the quadratic form of a multiplied with norm of 2 norm of x squared, then maximizing this 4 form over the unit sphere, would just boil down to computing the largest singular value of a. Okay, so in that sense, it's related to a very basic linear algebra quantity, but unlike computing the largest singular value of a matrix, this problem is NP hard, and it turns out that if you now try to ask how well can you approximate this, which is something natural to ask for NP hard optimization problems, then it becomes very delicate. Like the things that we know are not strong at all, and I will talk about the things that we know about approximating it. It has to do with this quantum entanglement and work around that. actually the NP-hardness proof of this follows from something that I will also talk about. It follows some work of Gurwitz. And I think actually it's the same work that Avi likes to cite in the context of operator scaling. And that work he also showed that, or he showed a result that implies that this is NP-hard, and it's something that's so there's sort of you get a small you get something about the accuracy for which this problem is NP-hard, but it's a pretty weak bound, and if you try to approximate it, then things become much more intricate, and that's part of the things I will talk about. The other things I wanted to mention. Right, and so the reason why I'm interested in this is it turns out that this problem is related in interesting ways to the unique games conjecture, and especially the graph theoretic variant, which is small set expansion. And it's related to the problem of a basic problem in quantum information theory, which is called quantum separability. And it's also related to this question about the power of unentangled quantum proofs, which the notation for this is QMA2. So that's the kind of problems that you can solve, you can certify with two unentangled quantum proofs. I will define this later on. And there's a question of how it relates to, say, exp problems you can solve in exponential time, or problems where you don't have, or where you can certify without with just one quantum proof. Sorry, I'm not sure if I said. So here, this is two unentangled quantum proofs. Okay. So now. Okay, and it's important, like all these applications, they correspond to special cases of this problem, and it will be important to sort of understand to what extent the special structure of these polynomials that arise when when you look at these applications helps us in solving the problem, or does it, or if it means that the problem is still hard. Okay. Now let me talk at a high level about the results. We'll see. And so first I want to talk about non-results. So things that, what I mean by that is things that you wanted to show but haven't yet been able to show. So those are some kind of the dream results. Or if you want to think about it as like that's sort of the program. Sorry. Okay, I forgot to say something which I wanted to say before. Right. So maybe let me just say something before. So in general, the results are about connections between the following questions. So one is the log rank conjecture in communication complexity. Which says that a communication complexity is determined by the sort of up to polynomial factors determined by the rank of the communication matrix. And then the problem whether the question whether there exists a quasi-polynomial time. Is there? Maybe let's give these numbers. So 1, 2. Is there a quasi-polynomial time? Time algorithm to find sparse vectors in linear subspaces? Yes. Right. So reals, yes. Right, and yeah. So, but you're right that over F2 finding sparse vectors over linear subspace is related to codes, minimum distance in codes, and but the kind of approach that we have, it exploits the fact that we work over the reals heavily, and also like that's sort of the applications that we want. So this is related to over F2.
Okay.
Yes. Yes. Yeah. Over finite fields, we don't say anything about this problem, and this is related to the Linear conjecture and the small set expansion, and more directly to small set expansion. And the third question is there a quasi-polynomial time algorithm to find low-rank matrices in linear subspaces? And that's also in the worst case and over the reals. Yes. Yes.
So this is that's Gurwitz.
Yes, exactly.
So
yes.
You probably mean something approximate or something.
No. But Gurwitz only shows that solving this problem exactly is hard. So approximately exactly. Yes.
Approximately is something that's close to
yes.
to lower. Yeah.
So right. Actually, it will be rank 1 matrices, and one form that we look at. Actually, that's the form that we will say something about. Is suppose that you know that if a linear subspace and it contains a rank 1 matrix. Now we want to find rank 1 matrix that is close to the linear subspace in Frobenius norm. And this is related to this entanglement or inseparability. So right, so separability is the quantum term for non-entangled. Means non-entangled states. And QMA2. Okay, so we would like to we talk about these connections between these 3 problems and these 3 questions. And so here are the dream results or the program that we have. So first, I would really like to show that 1 implies 2 and 3. So if the Lagrange conjecture is true, I want to show that it implies a quasi-polynomial time algorithm for finding sparse vectors in linear subspaces, which would refute the small set expansion conjecture. And it also, if the Lagrange conjecture is true, it implies that you can find low-rank matrices in linear subspaces in quasi-polynomial time.
So somehow the log-rank conjecture is a conjecture about 0-1 matrices.
Yes.
Questions 2 and 3 are, is there anything that's 0-1 about it? Because log-rank conjecture is false if you relax it.
Yes, so yeah, that's a good point. So we, it's true that that those questions are not exactly about 0-1 type things, but it's not the case that. But in some sense, that's the hardest case for these problems, that you have the 0-1 kind of behavior. And so there are so you have conjectural statements that are not ruled out by the fact that the log-rank conjecture is false over general matrices, but would still give algorithms for these kinds of things. But we don't know how to prove those statements.
But somehow the log-rank conjecture seems to be about how few low-rank 0-1 matrices there are.
How few?
It's not. It's somehow there are few low-rank 0-1 matrices, and because of that they have a lot of structure. That's what the log-rank conjecture is.
But it's not because it's few. It states that there are no interesting low
Right.
rank 0-1 matrices except those that come from partition.
Yes.
Right.
That's
And
what it says.
right. In some sense, that's like we want to exploit those partitions algorithmically for.
You will have a concrete result.
Yes,
along
sure.
this line.
Yes,
So
yes.
you'll see
Allow as 0-1 plus minus epsilon. It's not true.
I mean,
Exactly between minus 1/100 plus 1/100.
Definitely, if you allow
So-
most of them to be,
so
if you allow some exceptions, then I think
But
that
each one is roughly 0, roughly 1.
yes. I mean, like okay. So things that also again, in communication complexity, you want exactly monochromatic things for these kinds of things, and that's something that we don't need at all. And
I think approximately 0-1 in Frobenius would be completely false.
You will have a
That
concrete.
it's
Yeah, we-
close to being 0-1.
You will have a concrete result. You will see the connection.
Yes, yes.
even though-
Yes, but yeah, you're right that I mean that's sort of some problem that that these I mean we don't know this implication yet, and I think the main issues are different from this 0-1 issue. But it's of course also an issue, and okay, and then it would be nice to prove the log-rank conjecture, and then get these quasi-polynomial time algorithms, and maybe in general. So what's the kind of connection that that you hope to prove? That so here the log-rank conjecture asks you to prove a bound of the communication complexity of a matrix, bounding it by the logarithm of the rank of the matrix, and suppose that you could bound it by some function f of the rank of the matrix. So this kind of a bound. So if you have this bound for all for all m, then this implies. So basically, I want to justify a little bit what the kind of okay. So a priori, this seems completely absurd, but so here I want to justify a little bit what's the kind of connection that you could hope between the log-rank conjecture and these problems, and And so the kind of implication that you could hope to show is that if if you have a bound of this form for some function f, that this implies an algorithm with running time 2 to the f of n for these problems. now you see that if f is a polynomial in the logarithm of the rank, then this would be quasi-polynomial time, and but if f is like a faster growing function, then this would be a slower algorithm. And okay, so these are the kind of that's the kind of things that you would like to show. Now let me tell you what we can actually show. So basically we can maybe. So the actual result is is this kind of implication for the case for the kind of for the best known function that we know for which we know this inequality. Okay, so so we translate the best known bound which is that the communication complexity is at most the square root of the rank of the matrix. 2 to the square root n time algorithm to find low rank matrices in subspaces. Yes.
If you have an algorithm for 2 and 3, do you automatically get the UGC for the same running time, or is it just similar?
Okay, so if you have an algorithm for the problem in point 2, you get a corresponding algorithm for a small set expansion. The connection to unigames is not as direct.
It's wishful thinking.
Yes. Yeah, but I mean, the reason why we look at small set expansion is because we think it's related to the unigames conjecture.
And this result is really about rank 1, or as well?
Yes. Right. So maybe let me write this rank 1 matrices. Okay. So now.
For those who are not familiar
Yes.
with things, maybe you can say two words, what is the low rank conjecture?
The log rank conjecture. Yes. So the log rank conjecture is that. Yes. Is that the communication complexity of some communication of some two-party function is bounded by the logarithm of the rank of this communication matrix.
Maybe you should explain what is
Okay. So.
Actually, yeah, maybe okay.
And,
but this is not so. I mean, this
right.
you will not use this.
No,
Or you
I mean,
will use it.
okay. So I guess we will.
If you're going to define everything when you start your professor.
Yes. So yeah, but maybe just to so this here asks you to partition the matrix M into a small number of monochromatic rectangles.
M is a 0-1 matrix.
M is a 0-1
And
matrix.
you just need to partition it to a few subrectangles that are either all 1 or either
Partition, you
all
mean to
0.
write as a sum?
You can write it as a sum or just think pictorially. Yeah.
Okay.
CC is a log of the number of the time.
Yes.
Yeah, this is the log of this number.
So if you have a low rank 0-1 matrix over the reals, then you can partition it into a small number of vectors, which are rank 1.
Right. So now, so let me sort of talk about these. So the connection to these to these communication kind of things comes only later. So let me now talk a little bit about these two problems. So let me first talk about finding sparse vectors in linear subspaces. and also how it's connected to this meta problem of maximizing a homogeneous polynomial over the sphere. So we have a subspace W of Rn, and we wonder if there's a sparse vector in that a sparse non-zero vector in W, and it turns out that for so this connection to the small set expansion question, so this is about finding small sets in graphs that don't expand. For that connection, there's a particular way of measuring sparsity, which is some analytical way of measuring sparsity. And so we say that if you have a vector x in Rn, we say that it's analytically k-sparse if the 4 norm of the vector raised to the 4 is at least 1 over k times the 2 norm of the vector to the 4. And you can check that if you have a vector that is 0 everywhere except for k places where it's 1, then this is this would be an equality. And just to maybe clarify this notation, so the 4 norm is the sum of the 4th powers of the entries of the vector raised to the 1 over 4. So if you raise it to the 4, it's just the sum of the 4th powers of the right. So if you have a 0, 1 vector, then this just counts the number of non-zeros. So this would be k. This would be k squared, because this is raised to the 4, and so you see that if you divide by 1 over k, then you have an equality. And if you have a sparser vector, then this 4 norm tends to be larger compared to the 2 norm. So this is like a reasonable analytic way of defining sparsity. And so now the problem that we
0, 1. So if you have one very sorry, like a clear on both sides.
right. No, so another way to think about this is any k-sparse vector will satisfy this inequality. Okay, any vector that has most k non-zero coordinates will satisfy this inequality. That's some Cauchy-Schwarz kind of bound. Okay.
The question is, if a vector satisfies this inequality, what does it say about this?
Yes, so then it means that that in some sense the mass comes from k of the coordinates.
There'll be other coordinates. All coordinates can be non-zero, but the total mass.
And yes, and this right, and so this so it means that you could truncate the vector, truncate some small coordinates of the vector and get a actually sparse vector. And it turns out that this notion of truncation is exactly compatible with the problems around the Unigames conjecture. So therefore, that's the reason why we like to study this notion of sparsity. And now the problem associated to this is so here is the problem.
This is also the notion of truncation used in compressed sense.
Yes, but typically there you compare 1 and 2 norm for some.
So there are various.
Yes.
I guess they're also comparable. But here you do L2, or you zero out the small coordinates.
Yes.
In absolute value.
I mean, okay, it's a little bit delicate to like you have to do the truncation in the right way. Maybe consider all possible truncations and show that one of them works.
If you add a constant here to one side, it changes anything, or it's?
Second?
If you just add a constant like 10 somewhere, it changes something.
Like you add
10K.
10k. I mean, then it's just
K is different. No?
yeah. It's.
Oh,
I mean that's a definition.
I see. Okay. Oh, okay.
So yeah, that's a definition of the term analytically k-sparse. And so the problem that turns out to be related to the small set expansion question is the following. So given, it's a promise problem. So given as the subspace W, and the promise is that there is a vector in W that is epsilon n analytical. Sorry, it's analytically. Okay, some of this a little bit cumbersome to write. Epsilon n sparse, and the goal is to find vector x tilde in W that is analytically epsilon prime n sparse, where epsilon prime is just a function of epsilon that goes to 0 as epsilon goes to 0. Okay, and if you if you could solve this problem for some function epsilon prime, then you could also solve this problem that is related to the Ine-Games conjecture. So here the theorem. So this problem is harder. Yeah. So the small set expansion problem reduces to this problem.
You have probably some additional structure on the subspace W.
Yeah, actually,
The arbitrary.
that's true. So the subspaces will come from graphs in some way, but the thing is that we the hope is that you don't have to exploit that fact.
Yeah.
And right, so maybe one remark is that there's an algorithm that solves this problem in time 2 to the root n, and the reason is that if it turns out that if W has a dimension more than root n, then you can always then there always exists an epsilon prime analytically sparse vector for generic reasons. You don't need the promise. And if the subspace has dimension less than root n, then you can brute force in time 2 to the root n to find the analytically sparse vector. And it turns out that if you take this idea and sort of go with it a little bit, then you can recover the kind of sub-exponential time algorithms that we know for small set expansion. So in that sense, this problem, it still has this, like small set expansion has the property that it has sub-exponential time algorithms.
2 to the n to the epsilon.
Yes, yeah. So you get 2 to the n to the epsilon if you, right, if you change the notion of analytically sparseness in a way that would still be compatible with small set expansion.
So once you know what the big coefficients are, it doesn't matter that they're actually 0 or 1.
That's right. Okay. Yeah, but maybe one more remark. Yes. So how is it related to this problem upstairs? So maybe it fits in here. Clearly the optimization problem. If you want to think about it as an optimization problem, what you would like to do is to maximize the. You want some vector that is in the subspace, and this forenorm is large. And it turns out that if you would maximize the project, let me just write it. You project x to the subspace, take the forenorm to the 4, and you maximize this over all x that are unit vectors. Then this, this quantity tells you what's the analytically sparsest vector in the subspace W. And it's a little bit. So there's one. I mean, a priori, I should also, the constraint should be that the projection of x has 2 norm 1. But it turns out that that's you don't have to project x in this constraint. You don't have to project x. It will it sort of will be automatically satisfied because the projection can only decrease the 2 norm.
What do you maximize it? What is it?
So this is the projection of x into the subspace W, and I'm taking the 4 norm to the 4, subject to the constraint that x is a unit vector. And notice that this guy is homogeneous polynomial of degree 4. So sort of is of this form, like upstairs. Okay, so this is a special case of the problem above that is related to some problem that we care about, and you see that it has some special structure that you might be able to exploit. So now. I want to switch to a different problem, which is or different question, which is quantum entanglement. Okay, and just as I'm not sure if there are any quantum people in the audience, so I will do very bad things. First of all, I will talk about real vector spaces as opposed to complex vector spaces, which you're supposed to do in terms of, if you're doing quantum things. And I will not use the bracket notation, which is also a big problem. Yes, no, but so if you try to submit a paper to a quantum conference without using quantum bracket notation, yes, they will get upset. Okay, so yeah, let me just see what I wanted to tell you about. Right, so the basic object is a density matrix. Say on Rn. And this is just an n by n matrix. And it's positive semi-definite. And has trace 1. And this, okay, why do we care about those things? So it turns out that those matrices, they describe the state of a quantum system that has n ground states. Okay. So that's a way how to describe the state of a quantum system with n ground states, and this is this generalizes the notion of probability distributions. Where you have n atoms in the distribution, and it generalizes in the sense that if you look at density matrices that are diagonal, then you can interpret the entries on the diagonal. They will be non-negative and sum up to 1. You can interpret them as a distribution over the ground states, but density, but in the quantum world, you also have these the states that correspond to non-diagonal matrices, and that's in terms of the main difference between classical and quantum mechanics. What's going on here? Okay. Now now if you have if you sort of have two different quantum systems and you bring them together and you try to understand what's the joint, how to describe the joint states of the system. So you have a system with with the D sub A ground states, and another system with D sub B ground states, then the joint state so now you will have D times the number of ground states that you have will be D sub A times D sub B, and so that means that the joint state will be a density matrix on R to the D sub A tensored with R to the D sub B. Okay.
So are you taking the ground states to be orthogonal to each other?
Yes.
Okay.
Okay. Now, now we're interested in the notion of entanglement between these two systems, and it's easy to define the things that are not entangled. So we say that the state a set of separable states on R to the D sub A tensored with R to the D sub B. It looks like the following. So the notation is SAP of D sub A and D sub B. And this is the set of all, this is the convex hull of all states of the form XX transpose tensor YY transpose, where X is in, is in the pure state of the first system, and Y is a pure state of the second system. Okay, but in terms of linear algebra, this is just the definition. And so
unit vectors.
say again?
Unit vectors.
Yes, you're right. Right. So then these are density matrices, but they're not all density matrices, and you take the convex hull of just those density matrices, and so this I think the intuition is that so for these separable states, the interaction between the two systems has a classical nature. Okay, and so if you but maybe it's good to see a state that is not a density matrix that is not separable. So an example of an entangled state, non-separable.
Just take a matrix with 1 in one place and 0 everywhere else.
Say again?
1 in the first coordinate and 0 everywhere else.
That's
That's separable.
separable, yes. No, I wanted an example of a non-separable state.
Fourier matrix.
Fourier matrix. Okay, I'm not.
Be a rank 1 matrix.
Yes, exactly. So yeah, a rank 1 exactly. So a rank 1 matrix that sort of goes across, that is not a tensor product, right? I mean, those are also rank 1 matrices, but they. Okay, I'm not sure if you see that. That's a rank 1 matrix, and they tend to be they happen to be separable. But if you take now a rank 1 matrix that corresponds to, a vector in this space, which is not a tensor product, then you get something that is non-separable. And the worst example is the following. You take the sum of EI tensor EI, so that's the standard basis, and times its transpose. So that's, I think this.
What is EI?
So EI. EI.
Same bucket.
So here you have, you know, here. Okay, so this is right. So this would be, you know, a density matrix on RD tensor RD. But that is not separable. It's also called the maximally entangled state. And right, so you know, so this guy is, you know, lives in the space, but it's not a tensor product, okay? Because you have the sum over all the I. Okay, and so the associated question here is, you know, if suppose now I give you a matrix, a density matrix on the, you know, for the sort of a joint density matrix, and I ask you, you know, can you tell whether it's separable or not? Okay. Erase this. And it was so the problem that Gurwitz showed to be NP-hard. It's usually called quantum separability. So given some density matrix rho on RD tensor RD, let's say, you know, distinguish between the case. Okay, maybe it's just very simple. So decide if rho is separable or not. Okay, and the problem that we'll actually talk about is a somewhat a dual problem to this. So the set of separable states, you know, is a convex set, and so the separability problem asks you, you know, it gives you some rho, and it asks you, you know, is rho in the set or not? So you want to distinguish between, you know, the case that rho happens to be in the set, and the case that rho happens to be outside of the set. And the related question is, you know, given some linear functional, you know, find a separable state that that maximizes this that goes as far as possible along the direction of the linear functional. It maximizes the linear functional.
Natural optimization.
Yes, yes. So these two questions are related using the fact that, you know, if you for convex sets, the problem of testing membership is closely related to the problem of optimizing linear functionals over the convex set.
This convex set is not given by bounding.
Yes, yes, but the equivalence between these two, or the relationship between these two problems, holds for arbitrary convex sets.
Sure, yeah. No, I'm just saying it's not very convenient to optimize over a set that's given just as a convex problem.
Yes, yes, that's right. Yes. Right, and this is called the sometimes called the best separable state problem, and that's the problem that we will deal with the most. Yes, and right, and actually the thing that sort of is most relevant from a quantum point of view is that you have is that the vector, you know, corresponds to a matrix that is positive semi-definite and has nice eigenvalues. So that's those are called measurements. So I'm given some matrix M on RD tensor RD with property that, you know, M is positive semi-definite and has eigenvalues bounded by 1. So those are called measurements. Yeah, and the promise is that there exists some rho in some separable state rho that such that the linear functional corresponding to this matrix is at least C. And the goal is to find
Rho is this square by this square.
Sorry. Yes. I think this. Yeah, this should be fine. So you're asking. So I'm thinking of M as a linear operator. Yes, on this subspace. Yeah. Right. So M is a d squared by d squared matrix, and rho is a d squared by d squared matrix. We're trying to find the separable a separable d squared by d squared matrix that maximizes the correlation with rho.
This is matrix multiplication, M times rho?
Yes, and this is a natural inner product for matrices. And the goal is to find a separable state such that the correlation is S. And so this is so C and S are parameters of the problem. C is called the completeness, and S is called the soundness. And the relationship between those numbers is that S should be bigger than 0, less than C, and C should be at most 1. Okay, and we will shorthand denote this problem by BSS for best separable.
The first one is obvious, right, given the conditions.
Yes, exactly. So I mean also the fact that that this S should be bigger than 0, because otherwise any rho tilde will satisfy this. So this is right. So these numbers, they are natural between 0 and 1. Okay. So what do we know about this problem? So as I said, Gurwitz showed that this problem is NP-hard. And now, if you choose, and the NP-hardness corresponds to the case where it basically asks you to solve the problem exactly, which means that C and S are extremely close together. Like I think the best known NP-hardness result is for 1 over poly of D, and the result that I want to highlight is the following by following a hardness of approximation result by Haro and Montanaro. I think from 2010. And what they show is that this problem, even with completeness 1, and let's say soundness 0.1, has no, requires time, superpolynomial time, d log d, assuming, or unless the ETH fails, which means that 3SAT has algorithm with running time 2 to the little o of n. Where n is the number of variables.
So this is for constant C and S.
1 and 0.1. Yeah. Yes. So the fact that the hardness holds for 1 is makes it stronger. You can also make the soundness to be quite small. not quite polynomially small, but sort of close to polynomially small. Okay, but that's the best known hardness result that we have for this problem. That gives this quasi-polynomial time thing. Turns out that this hardness result. Okay, so let's maybe say first how, so it's also clear that this problem is again an instance of this general problem, because the way so rho comes from the is a point in the convex hull of these guys. So clearly, the rho that maximizes this. So if you think about this as an optimization problem, you're given M, you try to maximize this over all rho, and because the vertices of the set that rho comes from are these points, XX transpose tensor YY transpose, it's enough to look at those points, and now you see that. If you look at the trace of M times XX transpose tensor YY transpose, then this is a homogeneous degree 4 polynomial in the variables x and y. Okay, so this is some function fxy for homogeneous degree 4 polynomial f. And so your goal is to maximize this over all vectors such that x and y are unit vectors. And so in that sense, it's an instance of the problem above. And you have some additional structure, which namely that you know something about M. In particular, you know that M corresponds to a matrix with eigenvalues between 0 and 1. And that in some sense, gives meaning to these. I mean, this one here, this one, corresponds to the fact that it's interesting because it corresponds to the fact that M has eigenvalues at most 1. So in particular, it means that if in the completeness case, if it actually means that if you look at that rho has to live, or the vectors x and y, they have to live in the top eigenspace of the matrix M, where the eigenvalues are equal to 1. Okay, so
What do you mean x and y? The M is this square dimension.
yes. So the top eigenspace will be these
contain x tensor y.
x tensor y. Yes.
Yeah, not
Yes. Okay. It turns out that this hardness proof of Haro and Montanaro, it also gives you some additional special structure for this M guy, which happens to coincide with the special structure that we wanted for this problem. So in that sense, this also implies also for this. So this hardness result also applies for finding sparse vectors in linear subspaces. Okay. And the result that I'm going to talk about is that at this problem, has a sub-exponential time algorithm. So with completeness 1 and the soundness 0.1, then it has an algorithm with running time 2 to the root n, 2 to the root d, where d is the this dimension. And notice that 2 to the d would be the natural running time, because the vectors. So the witnesses are really the vectors x and y, and those are d-dimensional. So there are d variables involved. So guessing those would take time 2 to the d, and what we say is that you can actually do it in time 2 to the root d. Right. So it turns out that you can also, the algorithm also works if you have a completeness smaller than 1. So say completeness 0.9. But then the running time will be a little bit worse. It will still be, the exponent will still be polynomial, sublinear in D, but polynomial sublinear in D, but not root D anymore. Okay.
So the way it's finding rank 1, the way it's related to Hurwitz results is that the top eigenspace of M you can compute. It's
yes.
You can think of it as a
I think
space of matrices, and in it you are looking for rank 1.
Yes, I think actually Hurwitz was interested in this problem, and then but the hardness but this problem is very closely related to the problem of finding rank 1 matrices in subspaces.
If it's 1, then it's exactly.
Yes, that's right.
If the completeness is 1, then you have the subspace you look for. Rank
Yes,
1.
yes. That was a question, or I don't? No. Okay, so now let me tell you a bit about the techniques, and which will also sort of come to this connection to log rank. Okay. So maybe just briefly mention without defining it for the purpose, for the sake of saving time. So. So these things are also closely related to this question of QMA. Okay. See. Yeah, maybe I'll not talk about this. So there's some connection to this question about what's the power of having two unentangled quantum proofs, and try to understand what kind of problems can I certify with two unentangled quantum proofs. So recall that NP is the problem. Corresponds to the class of problems that you can certify using a classical proof, a short classical proof. And there, for classical proofs, it doesn't make a difference if you have, there's no notion of non-entangled classical proofs. But and then there's an analog of NP for in the quantum world where you have quantum proofs. And there, there's a difference between, or there might be a difference between having, a single proof where you can have lots of entanglement, or the case where you're promised that you have the proof consists of two parts, and they're promised to be unentangled. Okay, and there's been a lot of research to try to understand whether this actually allows you to solve more, allows you to certify more things than if you just have an entangled quantum proof. And it's also, even trying to understand how it relates to other classical complexity classes is quite mysterious. And in this, it turns out this best separable state problem is very closely related to trying to understand the power of these unentangled quantum proofs. In particular, if you had a quasi-polynomial time algorithm for this problem, so maybe let me just write this theorem. So if you could show that this problem, let's say with imperfect completeness, has a quasi-polynomial time algorithm, quasi-p, that would imply that the kind of problems that you can solve with with unentangled proofs, unentangled quantum problems, unentangled quantum proofs, they are a subset of the problems that you can solve in exponential time. Also, so it's already known that if you have just two unentangled proofs, that's the same as having any constant number of unentangled quantum proofs. And
Is it really known? This,
what do you mean?
is it really known?
That
What you just said.
yes. So there's a theorem by that's actually what the main result of Haro and Montanaro. What they show is that QMA2. So if you have two unentangled quantum proofs, it doesn't give you more power than just having. Sorry, if you have more than two unentangled quantum proofs, it doesn't give you more power than just having two. Right. Okay, and maybe maybe just the last thing. And it turns out that this algorithm, it gives also some bound for it also allows you to bound the power of QMA2, but it's sort of it doesn't look that impressive. But it's the best bound that we know. So this bound here implies that QMA 2, I guess with perfect completeness, it's contained in problems that you can solve in time 2 to the n over 2, where n is the size of the witnesses.
Instead of just to the end?
Yes. So the square root here corresponds to this n over 2 here.
The dimension is to the end.
Yes. Exactly. Yeah. Okay. So now, no more quantum. So to get rid of the quantum thing a bit, and as we discussed, so if you're in this completeness 1 regime, when you're really talking about rank 1 matrices in linear subspaces. So let me just write this down. So the problem that we want to look at now is the following. So we're given a subspace of matrices and the promise is that there exists a rank 1 matrix in the subspace. And the goal is to find a vector x such that xx transpose is little o of 1 close to w, and it turns out that the right way of measuring this is in Frobenius norm. So you want that if you project this guy to the subspace, you retain almost all of the Frobenius norm. Okay, and we want to solve this problem in time 2 to the root d, but let me change the d here to n just because otherwise I will get confused. Okay, and the way we're going to solve this problem is using sum of squares. And I will give you a definition of sum of squares, but the nice thing is that you don't have to remember the definition, because we will talk about it at a more. Turns out that there's as a way to talk about it in a more conceptual and a conceptual way that it will be clearer. So we are interested in the. If you're trying to solve this problem, then there's a natural way to view it as a system of polynomial equations that we're trying to solve. And let me write down the system of polynomial equations that we care about. So one is that we want that XX transpose should be in a subspace. Now, and so this will be polynomial equations in X. So now one way to write this as a polynomial equation, a natural way to write it as a polynomial equation is that if you project XX transpose to the subspace W, then you should get back XX transpose. And notice that this is so W is as our input, and X is our variables. So this is a degree 2 polynomial equation in X. And another equation that we have, which turns out to be convenient, is that X should be a unit vector. Just for to avoid the 0 guy. And now we're trying to find a solution to this system of polynomial equations. And what sum of squares does, so sum of squares is an algorithm that gets as input a system of polynomial equations and outputs. We know that this guy is satisfiable as a solution. What sum of squares on this input outputs is an object that looks like a distribution over solutions to A, over solutions to the system. And okay, now there's sort of this. What I have to specify is in what sense does the object that it outputs look like a distribution over solutions to this system. So, and to describe this, I need a little bit of notation. So suppose that you have suppose that D on the sphere on the sort of unit sphere of Rn. Suppose you have a function D that is finitely supported. Okay, and this what I would like to say is that that D is a distribution over solutions to the system. In the sense that if you look at the guys in the support of D, D of X gives me the probability that that X gets drawn in the distribution. And now, but the thing that we will be able to compute such a function, but it will not be a distribution. It will just look like a distribution in many ways. And there's a notation that is very convenient, which is the formal expectation with respect to D, and for a function f. And so this is just the sum over all. You just sort of just to formally use the same definition as for the expectation under a distribution. So f of D of x times f of x. Okay, so this is a formal expectation, or sometimes called, also called pseudo expectation. And okay, so that's a notation that I introduced. That's shorthand because I don't want to write out these sums all the time. And now what is that D satisfies? So D satisfies that the formal expectation of D of f is non-negative for all f such that there exists a simple proof that f is non-negative over the solutions to A. Okay, so I want this the function that sum of squares outputs has the property that these formal expectations are non-negative whenever there's a simple way of proving that those constraints imply that f is non-negative. Okay, and now the formal definition of what's a simple proof it will not be relevant at all for the talk, but let me just for the sake of completeness, I think obligated to write it. So what's the notion of a simple proof? So we say that right. So there's a degree D proof, and the notation is like that. And D is the measure of how simple the proof is. It quantifies how simple the proof is. If so that's the definition. We say A proves f is non-negative in degree D. If
Can you walk over the rings?
say again?
You walking here over?
Yes.
So it's not even necessary that f has a proof. Okay, I'm waiting
I mean.
okay, I'll ask it in
Right. I mean, I think if in some sense, if you care about doing things exactly, even just deciding whether f is non-negative or not is a non-trivial problem. Right. So the condition is that if there should exist polynomials p and q such that the degree of p and q is at most D. And what I want is that f plus p times this guy plus it will look a bit funny, but that's just how the algebra works here. So this should be a sum of squares. Okay, so P and Q are polynomials. Q will actually be a matrix, or a matrix valued polynomial. And so the way you should think about it is that P is some way of combining, taking this constraint. And Q is some way of combining this equality constraint, and this equality constraint of matrices. So the right way of combining these constraints is by in this way. And notice that if I look at the x that satisfy the constraints, then both this and this are 0. So these things are 0. For all x that satisfy the constraints, so it means that over the set of solutions to A, this is actually the same function as f. The function that I wrote here is the same as f, and what I ask is that f is a sum of squares. That there are that this new guy is a sum of squares. There are polynomials g1 up to gr such that this guy is equal to g1 squared plus g2 squared up to gr squared.
So now I'll ask you a question. So if f is non-negative, do we know that there exists such P and Q?
So
And of some degree.
okay, so it's a good question. So right, so in this setting that's true. So if f is non-negative, then
I think it's not true that you can express f as a sum of squares over the list
No, not f, but there are the multipliers that. So this right. So this follows from. So here we work in a compact setting because we have this constraint, and in the compact setting there. It turns out that these proofs always exist for simple reasons. If you're in a non-compact setting, then things are a little bit bad. But things get more subtle. But in the compact setting, this is true.
With degree n.
Actually, no. I think like here you might need higher degree because it might depend on the coefficients that you have here. Yeah, it's not the Boolean setting. Yeah, exactly.
Yeah, but if you are over R, then the degree is bounded because it should be two polynomials that are equal to one another, and then the degree on the left hand should be.
Yes, but it's not just n. I mean.
Yeah, because of the P. Okay.
Yeah. I mean, there will be some coefficients. I mean, it will also depend on W. Okay. So and there might be a sense that it might be that you can only prove that f is at least minus epsilon for all epsilon, something like that. But let's not worry about this. So that's that's a notion of. So this is one way of proving that f is non-negative over the set of x that satisfy these conditions, and that's our notion of a simple proof. And what this guy satisfies, it's just that for anything that you can prove in this simple way, the expectation will be non-negative under the distribution. It turns out that those proofs, they are really quite intuitive, or they correspond. It doesn't look like it, but they correspond in a surprisingly good way to the kinds of proofs that we like to do in the real world. And right, and then so now.
The algorithm outputs D with a small support?
Yes, so right. So in something it has to do it, right? Because otherwise it would not be efficient. Right. So maybe let's talk about the running time of the algorithm. So if you want something that is consistent with all proofs of degree D, then the running time of the algorithm will be n to the order D, and it also means that the support will be n to the order D. Okay.
So then it could be that D has no solution in its support. Otherwise, it would just give you a solution. You just go over all of them.
Yes. I mean, you only know that, right? You know that it will be on the points in the support will be on the sphere, somehow because the sphere is nice, but yeah, they will not necessarily be in the subspace. So this condition will not be satisfied by the points in the support. So actually, yeah, if you now try to find an algorithm that exploits this D in order to solve the problem, it's actually not a good idea to look at the support, because it's not. There's a lot of freedom there. Like, it's not like. In some sense, the things to look at are those expectations. They sort of give you more information about the problem that you're trying to solve. The support doesn't, or at least from as far as we know, doesn't give you any good information about the problem that you're trying to solve.
Where does the dimension of W enter?
The dimension of W doesn't enter at all anywhere here.
So the solution will not depend.
The solution. No. I mean the solution will depend on. I mean this D here will depend on W because the kinds of proofs that because the kinds of things that you can prove, they will. They do depend on W. So W, the projector onto the subspace appears here.
From this you can get X? Is that
Right. The goal is that to show that if I have such a D, then I can find an X that satisfies this condition.
This is a rounding problem.
Yes, exactly.
You want to run this D equals square root n.
Yes, exactly. D will be square root n. Yeah. And right, and now right. So now I can tell you a little bit about the connection to how the log rank thing comes in. So so maybe I think I should. So we should finish at 12:15 or something.
12:30.
12:30.
But if you
Okay.
you need some more minutes, it's okay.
Okay. So right, the connection to so here's the thing that we will use from this thing about log rank. So there's a theorem by Lovett which says that if M is so let M be a 0-1 matrix. Or okay, let me formulate it a little bit differently. So suppose that you have a matrix U, be an n by capital N matrix. Think of n as smallish and capital N as very large, maybe something like 2 to the n, 2 to the little n. Okay, and suppose that U transpose is 0-1. Let's see, did I mess up the... I think that's better. So then what Lovett shows there exists some set of some subset of the columns of U that is quite large, has density 2 to the minus root n in this set, and it has a property that if you look at this submatrix of U transpose U, this will be little o of 1 close to rank 1. In Frobenius norm. And this is the same, so because we have a 0-1 matrix, I mean, this being close to rank 1 is the same as saying that let's see,
Maybe you need to take a subset.
so I'm just wondering if I am supposed to say again?
Maybe you need to take like a subset of half but it's like similar.
Ah, yes. Right. So once you have this, you can get something that right. Right. So you can also get. Right. I agree. Okay. And
Does that mean all of those columns in I are essentially the same? Or
Say
in
again?
the same direction?
No.
Yeah, not necessarily. So just maybe to clarify these things. So if you look, if this here is U transpose U, then we take a subset of the.
Just a submatrix. That's not enough. I mean, the intuition is that if you have a 0-1 matrix that has low rank over the reals, the only way it can look is that it's just a partition to pure rank. You somehow depending on the rank. All disjoint or one. So it's just a sum of disjoint subrectangles which are full of 1. conjecture, and quantitatively the best bound known is this.
Right.
If it's an n by n matrix, then it's 2 to the minus, 2 to the root n is the number of them.
But the composition to rank 1 is also over 0, 1.
Yeah,
Well, you don't
basically
have to
the rank
figure
one
out, yeah.
decomposition is also over, it doesn't have other real numbers that close.
Right. And okay.
But my point is that UI transpose UI should be a self-rank matrix.
Yeah, it will be a principal submatrix. Is that what your question is?
The rank
So in order to be close to a rank 1 matrix, that means that all of those rank 1 matrices have to be essentially looking in the same direction.
Look, you're looking at the submatrix, not the entire matrix. You're looking at the very small submatrix, just the minus slope and number of folds of
But even UI transpose UI, right?
Right. So maybe are you okay? We will also use the fact that you can look at this in a different way. That if this guy is close to rank 1, it also means that if you think of U sub I to be the ith column of U, and you sum up over those guys, that will be UI transpose. So this will also be close to rank 1.
Oh, I'm sorry. So the rows are sort of look like each other.
So did you mean that? I mean, those two things are. I mean, this submatrix being close to rank 1 is the same as saying that this matrix is close to rank 1 in Frobenius norm. And okay, and this so you. I see, and okay, and your intuition is that if this is close to rank 1, then it should mean that UI should all yes. So it turns out that yes, so this is not this in substance not what's happening.
Okay.
So
This is close to
so these two guys have the same eigenvalues. So being close to rank 1 means that the top eigenvalue is larger than the Frobenius norm of the other eigenvalues, the 2 norm of the other eigenvalues. And so because they have the same eigenvalues, if the top eigenvalues dominates here, the top eigenvalue will dominate here. Right, and okay, so it's a very good question by Marcus. So does somehow right? So this being close to rank 1 in Frobenius norm somehow feels like all of the vectors should point in the same direction. But this is actually not what happens, and it's also very important that this is not what happens, because somehow if that's what's supposed to happen, then you couldn't have the root n. You would need 2 to the minus n, right? Because if I take U to be just random 2 to the n random vectors, and clearly they will all be different from each other. So if you wanted to single out a good the same direction, then you could only get density 2 to the minus n, which would not be good. But the nice thing that happens is that basically what you want is that there should be one dominant direction, and all the others they should cancel. And they can cancel here because because we measure things in Frobenius norm so if you would measure things in trace norm, things would be bad, but because we measure things in Frobenius norm, somehow if basically maybe the way you should think about it is the canonical so here I'm not sure.
But it's not due to the closeness, right? Even if it was accurate, it would not mean. Even if it was exactly rank 1, it would not mean.
Okay, if it would it be exactly rank 1, then I think it has to be the case, because this is a PSD matrix.
Can you find inside something close an actual rank?
Say again?
Can you find inside something that is close to rank 1 an actual rank 1 matrix?
I mean, if you truncate, but not by taking a subset of the. I mean, you shouldn't expect to find. I think if you really wanted this to be rank 1, then you would have to take minus n here. Right, and now so one thing what we show is that which will probably make Mark unhappy is that you can remove this condition. So this work. Okay, so this will still be true for if for general matrix. You don't need this condition. you can still show this theorem. And
That's, you're conjecturing that, or?
no, this is what we show.
There are some bounds maybe of the sizes of the.
I don't think you need any bounds. Because it's but the interesting case is that the UIs are unit vectors. They all have the same norm. If they have very different norms, then it's
The UI, the columns or the.
the UIs are the columns of U.
So the ones of length small m.
Yes, yes,
We completely remove the 0, 1 condition.
yes.
Somehow meaning that this result is not really about the Lagrange conjecture.
I mean, I think on, yeah. I mean, this bound is not is not.
Nothing to do with the Lagrange.
Yes, that is true. But so the things that. And it's also easy to see that it's tight if you have if you have a general matrix. And the example would be take U to be just 2 to the little n random vectors, random unit vectors. So then it's sort of it's super symmetric now, and it's sort of clear. The best thing that you can do is, maybe I don't think it's a proof, but it's very convincing that it will be tight if you take U to be random unit vectors, because so then it makes sense that the best submatrix will be you should look at a particular coordinate and take all the vectors that are sort of unusually large in that coordinate. So all vectors where the first coordinate is bigger than you would expect. And if you're shooting for this 2 to the minus root n kind of thing, then so in a typical right. So maybe. I think it's useful to discuss this. So second?
In general, there is no error, so why do you say that it's impossible?
Right, but I think so. I think what happens is that the part where you remove the error. So he proves this as I think that's sort of the key technical ingredient, and then there's a cleanup phase where you use the fact that you're over 0, 1 and to make it from almost monochromatic to actually monochromatic. That's right.
And this I is constructible?
Yeah, that's also a good question. So it turns out that for us it will be important, or it will be relatively important. It will be important to know something about this I. It turns out that constructible is not exactly the thing that's sort of the most important thing about it. What we want is that it has low degree in some sense.
So now I'm not sure about the program, assuming proving the Lagrange conjecture and proving that the Lagrange conjecture implies is 2 and 3.
Yes. Yes. Okay. So I agree. From this picture, it doesn't make much sense. But the thing is that So it's quite easy to I mean I agree that sort of so I think okay, what you can say is that yes, so there is a tight example for this theorem, but this is but for the problem of that we are trying to solve, this finding a rank 1 matrix in a subspace, it turns out that you could that weaker conditions, then weaker things than what we require here would be enough. For example, if let me get this right. So for example, right. So here would be something that is conjectural. That yeah. So maybe a conjecture here is the following. So there exists 2 subsets, I and J, of n, such that they have quasi-polynomial density. n to the minus log n, or yeah, 2 to the minus polylog n. So quasi-polynomial density as opposed to sub-exponential density. And what we want is that ui transpose minus uj transpose. This should be close to rank 1. Okay. So this this is a okay, right? If I choose j to be empty, then you see that that you could get here 2 to the minus Rudin bound, just because of this theorem. It turns out that this so for this question, if you allow yourself 2 subsets and you look at the difference of the two, not necessarily disjoint. So I'm just saying that this would be enough for us for the application to the rank 1 thing. Say again?
You can pick them the same.
No, you want.
No, but then it's not close to rank 1. So close to rank 1 means that that the top eigenvector is significantly larger than the sum of the others. So if it's a 0 matrix, then the top eigenvector is not significantly larger.
So if you intersect in one place, the difference will be. Oh no.
Yeah. In some sense, yeah, no, but
No, but if you intersect in everything but one place, the difference will be rank 2 or something.
Let's
One
see.
column and one row.
No, but you align them. What's the meaning of this event?
J to be either.
So okay,
They
so.
are the same, and you align them.
Okay.
Somehow to match the
Yeah. Okay. So right. So this. Okay. So sorry. Yeah. This doesn't. So I think what I meant is this here. So now there are 2 n by n matrices. Yeah. So if you. So the thing is that now the Gauss the example, if you take the vectors, if you take u to be random, it will no longer be a bad example in some sense, because you can do something like Zeev is suggesting, that you sort of pick I to be all the guys where the first coordinate is large, and you pick j to be all the guys where the second coordinate is large, and then because you subtract things, there will be a lot of cancellations, and the resulting thing will be extremely close to rank 1, even if you to rank 2. Yeah. And actually, yeah. So this right. So this would be also fine here. So any constant rank would be good here, and this would be enough to solve this to solve our problem. And so somehow, okay, I would still say that this has some log rank kind of flavor, and it's different from the kind of thing that you want for the in the communication setting, but I think sort of. The questions are different, but they're related in the sense that they seem to be about the same mathematical or about a similar mathematical phenomenon.
But then if you're not using the alphabet, the 0, 1, then it's not really the same phenomenon, isn't it?
I mean, okay, so yeah, I guess I'm not sure how important this 0, 1 kind of.
Well, it's important for log rank, so.
No, but I mean, okay, so the things that just that if you take the most direct generalization for non-0, 1 matrices, then it turns out to be false. But it doesn't mean that there's no analog for non-0, 1 matrices that would help you to make progress. So for example, it's not clear to me that if you could show this, suppose you could show this, suppose this would be true, would it be clearly non-useful for log rank? I mean,
It's not using the 0. No, if that was useful for something about log rank, so maybe this would be useful.
yes, yeah, exactly. Because I mean, here you also didn't get exact monochromatic things to begin with, and then you could use the 0, 1ness to clean up. I mean, at some point the 0, 1ness has to come in, but it's not clear, at what point, the 0, 1.
Why does it by the 2 to the minus root n tight.
Okay.
Take,
Right. So if you take so this tight example. So take U to be all unit vectors, or 2 to the n of them. Now, it makes sense that the best thing that you can do by symmetry is to take all UIs that where the first coordinate is bigger than some threshold. And now, so now if you look at the resulting matrix, UI transpose UI, the way it will look like is that it will have one eigenvalue that is slightly larger than you expected. I think this will be tau squared. And all the other eigenvalues will be unaffected. They will still be 1 over n. So that's sort of how the eigenvalues.
so the tau will be some constant over root n.
Yes, exactly. And if you now want this tau to dominate the Frobenius norm, what you want is that tau should be n to the 1/4. But the expectation of this guy, this guy is typically plus minus 1 over root n, and if you want it to be bigger than n to the 1/4, you have to be root n standard deviations n to the 1/4 standard deviations away, and that's the Gaussian thing. It tells you that happens with probability 2 to the minus root n. And I think that will be the best set here.
Just one point to Adam's question before. Computing I from U may be an interesting or less interesting problem, but U is not given. Only M is given, or the product, right? This algorithm gets a matrix, not U.
No. So the thing is that so far we. So it turns out that the U. Okay. So now what? Okay. How? Okay. Let me now try to explain how this kind of theorem is related to solving this problem. Okay. So it turns out that the U thing, the way it will appear is very indirect. It will. So let me show you. So really, basically, what this problem of finding I will correspond to the rounding algorithm. So the rounding algorithm will be we'll try to find the I and use it to extract a solution from this funny object that sum of squares produces. Okay, maybe right. So I haven't gave this a name. So if D satisfies these conditions, then it's called degree D pseudo distribution. For the system of polynomial equations A. Okay. So now, how could you use this this kind of rectangle thing to solve this problem? So.
You're assuming you're given D.
Yes.
You're given D, so you're given the value of D on all monomials of degree D.
So actually, I want to describe it first in like by a thought experiment, which will make it a bit clearer. So I will describe an algorithm, that you can't implement efficiently, but that will highlight the idea behind the actual algorithm. So the first step is to find a distribution, an actual distribution supported on the solutions on A. Okay. Okay, so now this is a distribution over unit vectors. Okay, and now we can think of the support of this distribution as this matrix U. Okay, so this will so capital U will be the matrix that consists of the support of D. And now the theorem, and I can think of D just being if I maybe repeat some columns here appropriately, I can think of D as just uniform over the columns of U. And now the theorem tells me that there exists some I such that if I restrict to those vectors, then I get something that is close to rank 1. Okay, so now find I, subset of the, and actually, so the way to think about it now is that I is an event for the distribution. So maybe think of it as a subset of. Oops. Okay, I guess that's a common mistake. Okay, looks like a common mistake. Find a D subset of Rn. Find some subset of Rn with probability of I being 2 to the minus root n under D, such that if you condition on this event I, XX transpose is close to rank 1. And now the final step is just to output the top eigenvector.
I was a subset of the whole. Was not a vector. It was not a subset of the other.
Right, but I guess I'm thinking of this process of selecting a subset of the vectors as conditioning the distribution on a particular event. And this this event could be just the vectors that are in that. I mean, this I consists of the vectors that happen in the thing happen to be in the thing that you selected here. Okay, and now now it's easy to see. Now it's easy to see that if you would do these steps, you would output a vector that is close to the subspace. The reason is that so D is supported on solutions to the system. So now if you so it means that so it means that every x for every x in the support of D, XX transpose is in the subspace. And now we condition on some event and we average. So it means that this thing here will be in the subspace. And we have the condition that it's close to rank 1. Okay, and so it means that if we look at the top eigenvector of this guy, then we have a rank 1 guy that is close to this guy, which happens to be in the subspace. Okay. Okay, so now. Now, what do you have to do to make this into an actual algorithm?
So if it was supported on A, you just output anything, right? So it's not really
Yes. But so the thing is that so I'm just claiming that this is an algorithm that would output a correct thing. It's not. I'm not saying that this would be the most natural algorithm to output. But the nice thing is that there is now a clear way to make this into an actual algorithm that runs in time 2 to the root n. So the actual algorithm, will use a pseudo distribution. Okay, and now. So now I can. I mean, before this step is clearly not efficient. But now, if I allow myself to use the pseudo distribution instead of an actual distribution, then I can actually find such an object. Okay. And now, what I would like to say is that I can prove this. I can prove this theorem also for pseudo distributions. Okay. That there's an analog of this theorem that works for pseudo distributions, such that I will be able to compute this guy. Okay, and now so prove an analog. Now we need an analog of this rectangle lemma for pseudo distributions. And the analog will be as follows. So what we'll show is that there exists a degree root n polynomial capital R, such that if you and this guy is a sum of squares. Such that if you look at the distribution that you get by, or if you look at the function that you get by by multiplying d of x with this polynomial r of x, what we want is that this guy is close to rank 1.
What is u now? There's no u.
U. So. I mean, here was also no u. Okay. But right? If I think of the support of the distribution as my u, then this conditioning is selecting a submatrix of u transpose, and here what we want to do now for pseudo distributions, instead of selecting a submatrix, what we want to do is we want to give weights to the so the analog for actual distributions is that I want to change the weights for my for these vectors by some low degree function, such that so maybe let me.
How is it low degree?
I mean that will be the thing that we have to prove. So that maybe the analog in terms of the U business would be that we consider, instead of a UI transpose, instead of this guy, what we'll consider will be the sum over all I of R of UI times UI transpose. Okay, so we will show that for every matrix U, in particular, one thing that we will show is that for every matrix U, there exists a degree root n polynomial R, such that if you look at this matrix, it's close to rank 1 in Frobenius norm. And before we select a subset of the vectors, and now we give weights to the vectors according to a low degree polynomial. And the nice thing about that is that it also makes sense for these pseudo distributions. Like conditioning would not make sense because, as I said before, some of the support of these pseudo distributions is usually not something that you that is useful to look at. But this reweighing operation turns out to be something that's okay. Okay.
The degree is root. If you have a big N vectors, the degree is root of log n or root of big N.
So n here is the rank of the big matrix. So if U is a little n by capital N matrix, then it would be square root of little n.
The number of variables that you plug. The number of variables of the polynomial.
Yes, yeah. In this picture, right. It will be root of the number of variables. That's right. Okay. Sorry. Oh, yeah. So we used little n for the variables. Yes. Okay. Right. Okay. So now what?
Unit vector. The URs.
Yes.
So what you need you want to use the pseudo distribution of degree root n also. Right?
That's right. Yes. Yes.
So it's not, and then you reweigh with also root n.
Right. But then I mean I need So I will need a pseudo distribution of degree root n to show that this conclusion will hold. But but in some sense, once I do this operation, I don't really care about. So I guess one thing I will still care about is that this guy will still be in W. This is something that is true also for pseudo distributions. That if you perform this operation, you will end up with a matrix in W.
This is the degree bound matters or not?
For this, the degree bound matters. Yes.
Matters.
Yes. Because essentially, if you multiply this by some polynomial of degree of degree root n, then this output will depend on the root n degree moments of the pseudo distribution. And if you didn't have this consistency kind of requirement up to degree root n, then these root n degree moments would be undefined or could be arbitrary. So it's important that here you have a degree root n pseudo distribution, right? And now so what I wanted to do, not sure. Maybe I can give you a quick idea about how this works. I want to show you how to prove this analog of the rectangle lemma, not for pseudo distributions, but for actual distributions. But still, but you would still do this reweighing kind of operation instead of conditioning. And this contains the main idea, right? So the strategy for proving this would be to prove that such a polynomial R exists if you had an actual distribution. And then inspect the proof and show that all the steps of the proof used only things that you can also prove in this proof system. So the theorem is that for any distribution, and the theorem is nice because it seems to be very general. It doesn't have, it doesn't really have, it doesn't seem to be about the problem that we initially started out with. Distribution D over the sphere. There exists a root n degree polynomial R such that if you take the expectation under yes close to rank 1. In Frobenius norm. And so the proof is iterative. In some sense, the idea of the proof is it has to do with the fact what we saw, that in the random case you're supposed to look at one coordinate is large. So what and the idea is, we look at this distribution. If it doesn't satisfy, if it already satisfies that the second moment is close to rank 1, then we don't have anything to do. Now, so the interesting case is that that the second moment is far from rank 1. So maybe all the eigenvalues are 1 over n. And now we will try to find a polynomial r that increases one coordinate, or increases some coordinates, and now, in some sense, you could hope that you're done, because well, you will increase one coordinate that will sort of create one eigenvalue that is slightly larger, and all the and now, it looks like you're in this picture.
But you step out of the sphere.
No. I mean, here with this reweighing, you will always stay in this. Yeah. So I just change the probabilities. Now the issue with that is that if you create one large coordinate, that will create one big eigenvalue. But the worry is that that operation could also create, for some strange reason, many other large eigenvalues. And now you're not necessarily, now the resulting thing will not be close to rank 1. Okay. And basically the proof is trying to combat, trying to deal with that kind of issue. So the main claim is that either D already satisfies the conclusion, or there exists some degree root n r as a sum of squares, such that now we know such that we can increase some potential, and the potential we will increase is that that the norm of the expected vector of the mean of the distribution increases. 1.01 times the times the norm of the mean before. And now, if you can prove something like that, then you're in good shape, because there's a simple argument that shows that you can assume that this quantity is at least some 1 over polynomial in n. And now, if you iterate this claim, then whenever D doesn't satisfy the condition, you would increase this norm by a constant factor. But clearly this because you're always over the sphere, this norm is bounded by 1, so this can happen only a logarithmic number of times. And so it means that the number of polynomials that you get will be, so you will have at the end you will have a logarithmic number of polynomials r that you're supposed to multiply all together to get the final function r. And now to do this, what you can do is the following. Let's look at the second moment of this distribution, and let's rearrange things such that basically such that this coordinate corresponds to the mean. Okay, so we will do a change of basis such that this guy is some basically it will be square root of lambda 1 times the first coordinate vector, and then we will diagonalize the rest of the guys. So by doing some change of basis, we can make sure that the matrix looks like this. The second moment matrix looks like this, because if you're not already done, we can assume that the Frobenius norm of these guys is some constant factor times the top eigenvalue, or times this guy. Otherwise, this guy would be close to rank 1. And now, okay, and now the nice thing that happens is the following. So if you suppose that you sort the eigenvalues in this way. Now, if this happens, you also know that if you look at the sum of the first root n eigenvalues, this will be also bigger than okay, slightly confused. No, I think okay. I think this is correct. I'm a little bit. Yeah, I think this is correct. So like if you if you square this, then you get the product of these you get n square n terms, and each being bigger than and each you sort of course you dominates one of these guys. So this squared is bigger than that squared, and now what this means is that there is this root n-dimensional subspace corresponding to these corresponding to these first root n coordinates, such that yeah, what does this condition mean? So this thing here turns out to be exactly the expected 2 norm of the vector x if you look at the coordinates 2 up to root n. Okay, this is exactly the same. So it means that what we know is that our distribution, if you look at this very small subspace, the expected norm there is comparable to the top eigenvalue, and now what you can do is basically you can brute force things in this root n-dimensional subspace, and create this polynomial R. You can find a polynomial R of degree root n now that achieves the following, such that the norm of the mean after the reweighing of these coordinates is at least the expected norm before the reweighing. Right. So this this is quite intuitive. Like I tell you I have a distribution, and in this subspace, and if I look at these coordinates, the expected norm is blah. So now I should be able to to condition on an event such that such that the norm there is basically sort of pick out one vector that has this. Just I pick out one vector that has this norm, and it's not hard to show that instead of conditioning on some event, you can also do it by using root n degree polynomial. But the thing is that like now you work in a root n-dimensional subspace, so things are very easy. So things are much easier than if you work in an n-dimensional space. And now you're in good shape because now what you have is that you know that in this subspace right. So the goal was to show was to show something like that. That the new, after reveighing, the norm of the mean is bigger than it was before, and now we created some norm of the mean that is omega 1 of lambda 1, and this turns out to be bigger than omega 1 of the mean that we had before. That's great. Okay, so now we created some mean in a subspace where we have a constant fraction of the mean that we had before. And notice that this subspace is orthogonal to the subspace the corresponding to the first coordinate, and our assumption was that the original mean was along the first coordinate. And so now what you can show is that the norm of the overall mean will be the sum of the two things. So the sum of the old mean and this. So this is the increment for the norm of the mean, and that shows this that you make progress.
So this is inspired by Shachar's book.
Okay, so that's a good question. So we had an initial approach that was inspired by Rothfuss's proof of Shachar's bound. I think I'm not sure if this appears in Shachar's proof, but I think Shachar I think there's some argument in communication, in this context that is similar to what we're doing here. So the correspondence between this proof and the proofs for the previous proofs is not so clear.
There is also a kind of amplification, but it's not clear.
Yes. I mean, so
it just there you would sort of improve the distance to rank 1, really.
Right.
Well,
Yes. I mean, here the
also here you do it, but
here the amplification is somehow to deal with some pathological cases where sort of some strange eigenvalues pop up for some funny reason. But I think like this picture that you try to increase one coordinate, try to make sort of, especially if I mean here if instead of choosing the first coordinate, if you choose a random direction and try to increase the coordinate along that direction, that's something that's what Rothfuss's proof of Lovett's bound does. And in some sense, what we are doing, we're choosing the directions that we are increasing. We're choosing them carefully, right? Based on where the mass is. Okay, so that's what.